Welcome to another Creo webinar. This Creo webinar, which is brought to you by Creo.space, is about the context of life in the universe, specifically about life and the scale of the cosmos. So let's begin. My name is Stephen Moises, and I'm the instructor for Life in the Universe. And this Creo webinar reviews scale of distance, of size in the cosmos, which helps us understand where life is with respect to everything else. It helps to have a map of what we are. You've often heard the term, we are stardust. It's an interesting phrase. It conjures up ideas of the synthesis of dust and gas in space, like in this image here, of the galaxy coalescing into a collapsing cloud somewhere, a clump that in turn, by gravitational collapse across vast distances, more than a light year, and the potential energy of that collapse brought into the center towards the formation of a star and a remnant disk of gas and dust around that star, which then goes into forming the planets, moons, asteroids, comets, etc. So out of this, we get a planet like the Earth, but it ultimately is stardust that is formed during the evolution of our galaxy, which evolves in the evolution of the cosmos itself, of the universe. The first and simplest atoms were only hydrogen and helium and a bit of lithium, beryllium, and boron. These were created during the Big Bang, the cosmogenic nucleosynthesis at the beginning of time. More complex atoms were created in stars. So heavier atoms with more protons and neutrons in their nucleus went into making elements that go into planet formation and biological formation. Things like sulfur, phosphorus, oxygen, nitrogen, carbon, hydrogen, iron, etc. Well, when a star dies, its atoms are expelled into space. And these are the dusty masses of clouds that are within the spiral arms of a galaxy. They appear dark because they attenuate light going through them. And this then goes back full circle so that a clump of some of this gas and dust expelled into the interstellar medium can then reform into a next generation star and planets around it. Many of the atoms in our bodies were created in the cores of stars. So everything around you was made in nucleosynthesis before the origin of our solar system. To begin to understand the scales of things, it helps to remind ourselves of scientific notation, which was invented in order to represent very, very large numbers easily and conveniently. So scientific notation uses the powers of 10 so that 10 to the 0 over here is the same as the number 1. At the top of this list, you will see 10 to the 1. Well, that is equal to 10. That means that there's one digit in the tens place. Likewise, 10 to the 2 would be 100, and so forth. We can go all the way up here in this notation. 10 to the 11 is just 11 zeros here in the following the number 1. So 100 billion can be expressed as 10 to the 11. Well, we can go in the other direction, of course, using the minus sign. So the 10 to the minus 1 is simply moving the decimal place such that we're in the tenths place. And then next would be into the hundredths place or percent. And here in the thousandths place or in the per mil, parts per thousand place. Well, how about we talk about scales? From where you're sitting to the lowest clouds above you in the sky, if that distance, just looking out the window, equaled the distance from Earth to about where Pluto is, the first very large object after Neptune, a trans-Neptunian object, that equals about 5.9 million or billion kilometers, excuse me. That's the distance from here to Pluto, almost 6 billion kilometers. Well, if you said that between where you're sitting and the lowest clouds in the sky is equivalent to the distance between Earth and Pluto, then the closest sun-like star, Alpha Centauri, which is 4.2 light years away, would be 4.2 times the distance that light travels in a year, also known as a light year, which is equal to 9.5 almost, times 10 to the 12 kilometers. So that distance, which is nearly 40 times 10 to the 12 kilometers, would be 40 times 10 to the 12 kilometers divided by 6 times 10 to the 9 kilometers, meaning that the distance is 6,713 times farther away than Pluto. So the distance where Earth is from Pluto would have to be multiplied over 6,700 times just to get the equivalent distance from Earth to the nearest sun-like star. So a distance from anywhere you're sitting to a typical cloud deck above your head is approximately 2.5 kilometers. So 6,713 times that is about 16,780 kilometers. That is approximately the distance from London, England to Sydney, Australia. So think about the difference there in the distance. In reality, there are probably things in the solar neighborhood like other trans-Neptunian objects besides Pluto, rogue planets, comets, even maybe a dark star. But the distances are vast. Here's a schematic map of our solar system from a distance. So the map shows here in the upper right, the sun and Mercury, Venus, Earth, and Mars here. And that zooms out from a much larger map showing the orbits of Jupiter, Saturn, Uranus, Neptune, and Pluto way out here. Compared to the galactic equator, our solar system is a little bit tilted. So that's what's represented here. And that tilting, actually, it changes over time as the solar system orbits the center of our galaxy, approximately once every 225 million years. Right now, the sun and our solar system is inside of a cloud, actually just left that cloud. It's called a local fluff, and that's what's shown here in this graphic. It's a cloud of interstellar gas that is extremely low concentration, low pressure. A handful of air stretched over a column that is like 100 light years long. I mean, it is so little gas, but it's more gas than what's around it. And the cloud also has motion. So although our sun's direction of motion is shown in this graphic, going here towards the upper right in this coordinate system with respect to the galactic center, the local cloud is actually kind of moving relative to us away, so outboard of the galactic center. So also this graphic shows the sun, Alpha Centauri, just below and to the right, galactic centerward, Eridani and Sirius here, a large blue star. But there are other stars in our interstellar neighborhood. So if the solar system is here at the center, here's again Alpha Centauri, 6,700 times farther away from us than Pluto is. There's some more here, Sirius, which I just mentioned, the blue star, and Epsilon Eridani, Procyon, Arcturus, Deneb, and even further stars, which are large and bright, like Castor, Aldebaran, Capella, and here's Vega on the other side. So this is just a small collection of stars within several tens of light years of us. We can step back even further, however, and see that, yeah, our solar system is part of this cosmic cloud, and the orbit of the solar system around the galactic center is 217 kilometers per second. It's very, very, very fast. So the solar system at this velocity completes a lap around the nucleus of the Milky Way, which is a barred galaxy here shown at the center, once every 226 million years. And it actually undergoes a kind of swinging motion in doing so, of relative to the galactic plane of about 5 to 7 kilometers per second, and towards and away from the galactic center at 15 to 20 kilometers per second. And like I said, the solar system is tilted with respect to the Milky Way galactic plane. So the other stars actually that are in our solar neighborhood are likewise tilted, but they're tilted in all different directions. So there isn't a coplanarity of spin and direction of stars. So our place in the cosmos, it's difficult for the brain to grasp just how incredible the scales are. Here's our little Earth within the solar system, which is not shown to scale, which is in the galaxy, our Milky Way galaxy. But our Milky Way galaxy is part of a group, local group of galaxies that is in turn part of a local supercluster that's in turn part of the fabric of the universe. And here's, of course, the famous Hubble Deep Field, showing that just for a tiny slice of sky where the Hubble Space Telescope was pointed at long exposure shows galaxies everywhere in all directions. So the universe has something on the order of 10 to the power of 11 galaxies. And our own galaxy has something on the order of 200 billion stars, or 2 times 10 to the 11 stars. So there are at least as many stars in our galaxy as there are galaxies in the universe. Now, birthplaces of stars are things like this, Eagle Nebula, where the ashes of dead stars blown out into the interstellar medium in the arms of the galaxy, then begin to gravitationally collapse in on themselves in their own mass and make, you see these little nubbins there that I've circled in red, where gas is gravitationally bound around young stars, and any gas that isn't bound, it's unbound gas around a young star, is being blown away by very bright active stars like this one here, blowing the gas away, just leaving behind a protoplanetary disk. These protoplanetary disks are the precursors of new solar systems. Beta Pictoris here is an example of one of the earliest such disk systems that was observed, and the central light of the star was blocked out, and you're looking at kind of a cross section of the nascent solar system around Beta Pictoris. These disks of gas and dust, of course, coalesce ultimately into sand-sized grains, then pebble-sized grains, cobbles into larger objects like planetesimals, which in turn coalesce and smash into one another in giant impacts to form the planets. Now, our planet recycles itself, and it doesn't have a history of this early time. And this is something that, of course, we discuss in the first course of the Collaborative for Research and Origins, which is Earth system history. And we have volcanism, weather, denudation, erosion, remelting, all of which erases this early history. So in order to understand what happened early in making the planets, we have to look at extraterrestrial debris, which is surprisingly common. About 20,000 tons per year fall on the Earth. And here's an example just from a decade ago in Chelyabinsk, Russia, where a meteor came in the morning and lit up the sky and caused sonic booms and explosions, which knocked out windows in housing districts in the area. Dust from this meteor was analyzed, and it's just part of this dust that is constantly raining down on the Earth. So we like to study these things because it tells us about early times. And of course, Earth is different, and the context of life in the universe requires that we talk about things like the chemistry of life and DNA, the molecule of inheritance. And this DNA is fabulously small. You need electron microscopes to see it. So it's at the other end of the scale. So it's really like the smallest things that are very important at our scale of the universe, the scale of molecules and chemical reactions, in this case of biology. And the Earth is a rich environment for life. The scale here is at the scale of ocean basins and the crust and the atmosphere interacting with the oceans, which interacts with the crust and allows for a living biosphere powered by the sun or powered by chemical energy from heat in Earth's interior. Hot springs, boiling water, very early types of organisms live in these places. And as we discussed in the previous course, in order for us to understand life, we have to understand the planet and how Earth has evolved and how the planet and life have co-evolved. Fossil records of life go very far back to even within the first 500 million or 1 billion years of Earth history, showing that life appeared very quickly on the surface of our planet. We also know that most life on Earth is microbial. You can't see it with your naked eye. You need a microscope. The origin of intelligence is something very recent in the history of Earth, the history of our solar system, the history of our galaxy, the history of our universe. In 13.7 billion years, it's only in the last 500,000 years or so, maybe the last million years or so, that intelligence, tool making, language making, history sharing intelligence leading to technology appeared. It appeared on our planet. It's interesting to wonder if life appeared on any other planet in our solar system, or perhaps in an icy moon in the outer solar system. But ours is the only planet, as far as we can tell, that has life in our solar system, and certainly the only one with intelligent life. But what about out there? Well, Mars has been an awesome laboratory to try to test ideas in the search for microbial life on other planets. Mars is a world which, although dissimilar to ours, it's only about 11% of our mass, and it is 50% farther away from the sun than the Earth is nevertheless compelling because it has so many Earth-like qualities. Ancient channels on Mars have been found that are almost certainly carved by water. Now, how long this water was running on Mars and when exactly continues to be debated. We have sent rovers to Mars. This is one of the first, the Viking lander. It didn't have a rover, but it did investigate the Martian surface for signs of past life. Of course, rovers are fascinating, fantastic, and extremely useful. They are our eyes and ears, and even, you might say, our taste buds sent to another planet, because we're looking around, analyzing, listening, and taking samples and trying to understand the composition of this planet. We have been very successful in placing landers on Mars, and looking at some of the images coming back, I mean, you can't help but draw analogies to places like desert environments of the Gobi or the Atacama or the American Southwest. But I mentioned also icy moon. The JUICE mission was just launched. It's to investigate the icy moons of Jupiter. It will begin sending back data at the beginning of the next decade. Maybe we can answer the question of whether or not life emerged out there in the darkness of the outer solar system. A place like Europa, it's the second moon out of the Galilean moons of Jupiter, shows fractured ice surfaces here. However way you want to think about the context of life, you have to think of the context of distances. We're not going to get anywhere quickly. We're limited by physics and how quickly we can get to someplace. It just takes time, even in our own solar system. And to think about getting to another star is really challenging. And we have so far to go. Even our best technology, we couldn't get to the next star in less than a few tens of thousands of years. So it's probably going to be robotic spacecraft that will ever get to another star. I mentioned the Hubble Deep Field. Even getting to the next star is simply just the tiniest step within the sea of stars just in our galaxy. And our galaxy is simply one of these many oceans of stars scattered throughout the entire universe. Looking back even further, the large-scale structure of the universe might tempt you to feel insignificant. Let me assure you that we may be very, very small, but that doesn't mean we're unimportant. There are planets around other stars. We know this. At last count, something like close to 6,000 stars have been found. This image here is, of course, just an artist impression of what some of those planets might look like. It may be a very, very long time before we get a picture element of one of these things. And many of these planets that have been found are found to be very, very close to their star. So it means that planets don't just form in place, but sometimes in the history of the solar system, planets can move and move very, very close to their stars. We've only very recently started to explore any of this. Remember your history. Just a few thousand years ago, we were stuck in the Iron Age, and before that, the Bronze Age, and before that, the Copper Age, and before that, the Stone Age. And in the Stone Age, did we begin to cultivate crops and raise animals? And that's only in the last 20,000 years or so. And the history of the human species is at least 10 times longer than that, if you just look at anatomically modern humans. So we're just beginning. Getting to another star is so difficult, it may not be possible. At least I think it may not be possible for humans to get to another star unless you extend our lifespans and genetically engineer us to go to sleep for centuries and then wake up and somehow survive the trip. Or you have us live very, 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 very long. But what do you do about boredom in these long journeys? Some civilizations may be so far beyond what we can understand. I mean, after all, our galaxy is something like 9.5 billion years old. The first stars of our galaxy could have had planets, maybe a little bit different from ours. We are not quite sure how different, but it's not out of the realm of possibility that there are systems that are 1 or 2 billion years older than ours that had technology long ago and have since harnessed the energy of their system and are as advanced to us as we are to a single-celled organism. So life might passively travel between the stars if bits and pieces of rock and so on are scattered out throughout the galaxy. And this is an idea, it's an old idea called panspermia. So far, we haven't found any evidence of this. To end, I wanted to give you a taste of life's context in the universe, and to think about the scales, not just the scale of time, but also the scale of distances. getting there is probably not possible for living things unless we change ourselves. But mechanical things, which have no short expiration date, might be able to make it.